Hello, class. This is Mr. Hart, and this podcast we want to finish up the reactions chapter of our textbook and cover some final terms that we need to know when we're describing reactions. And one of those terms is reaction rates. Okay, and so let's look at two different reactions that we're probably familiar with. One of them would be like a hand warmer. Okay, you ever seen those? You put them in your gloves, you shake them up, right, and it heats your hands up with the chemicals that are inside. Another one is like a firework or an explosion, okay, any type of combustion reaction, okay. Let's compare how fast these reactions go. So in a hand warmer, you obviously want this to last a long time, okay. A lot of them last for a couple hours, some even last up to 10 hours, or at least they claim they last that long. But the point is you don't want the reaction to happen too fast, right? You want this to last a long time. So this is going to be a very slow reaction, okay. Not only do you want it to last a long time, but you also want it to not go too fast because you don't want it to burn your hands, right? You don't want it to create too much heat. Okay, so when they design hand warmers, they want this to be a very slow reaction. Or in other words, the reaction rate is very slow. Okay, the rate at which the reaction is occurring among the molecules is going to be slow. As compared to a firework or an explosion of some kind, you want this to be a very fast reaction, right? You want this to happen almost instantaneously, right? So the reaction rate, or the rate at which the reaction is occurring among the molecules, is very quick. Okay, so it's kind of an intuitive idea, right? How fast our reaction is occurring. Okay, that's the reaction rate. So in class, we did a sugar cube lab where we dissolved sugar cubes in water with different conditions to kind of help us get an idea of how reaction rates are affected. And when we did that lab, we saw that these are some of the things that affect the reaction rate. Okay, so the temperature of the reactants is going to affect the rate. The hotter the temperature, the more quickly the reaction is going to occur. Okay, the concentrations of the reactants. Obviously, if you have more of the reactant, it's going to occur faster. The surface area of the reactant. Okay, this makes a lot of sense with the sugar cubes. If you have just the cube, okay, it doesn't have a lot of surface area, but if you crush that cube into a powder, okay, then it has a lot more surface area, a lot more can react at the same time. Okay, so this happens with all types of chemical reactions. Okay, the more the reactants are kind of exposed to each other, the quicker the reaction is going to occur. Okay, movement of the reactants in the sugar cube lab, we related this to stirring, the water in the mixture. Okay, that helped the sugar cube dissolve faster. Likewise, in a chemical reaction, if you move the reactants around, if you kind of stir them, you have some type of agent that moves them around, then that will make the reaction occur faster. And then the last thing that helps them move faster is what we call a catalyst, the presence of a catalyst. So we'll get to that in a second. But we want to make sure we understand these four things. Okay, so let's go back to the hand warmers example. Okay, so for example, in a hand warmer, one of the things they say is we said that the reaction would occur faster if there's more surface area. Okay, so in a hand warmer, for example, they're going to have little pellets of material rather than a powder because that's going to make the reaction occur slower if they have pellets, which is low surface area, compared to powder, which is high surface area. Whereas in an explosion, like a firework or dynamite or something like that, they want a nice powder so that they can have more of the reactant exposed at a given time, and so this reaction will occur faster. Okay. And so again, there's lots of different ways to make the reaction occur faster or slower. So chemists need to understand how these things affect the reaction rate when they design products like hand warmers or fireworks or anything they use as a chemical reaction. Okay, so you're going to want to know these, a couple things that are going to affect how fast a reaction occurs. Okay. Then we used a PhET simulation. We looked at some gas particles in a chamber and looked at how if we raise the temperature of that chamber, okay, then the reaction occurred faster as well. Okay, so hopefully this is making some intuitive sense that the higher the temperature that is in the reactants, the quicker the reaction is going to occur. Okay, now we said the presence of a catalyst. So let's talk about what a catalyst is. Okay, so a catalyst is a substance that increases the rate of a chemical reaction. Okay, so its job isn't to react with the other chemicals. Okay, its job is just to make the reaction occur faster. So if you've ever seen those little beef jerky like if you ever eaten a bag of beef jerky, you see those little bags inside that kind of absorb the oxygen. Those things have a catalyst in them that help the chemicals absorb that oxygen faster. Okay, and so that's one example I know of that is a application of this, is where they put a catalyst in there to help absorb that oxygen faster. Okay, and again, anytime you have a catalyst, the goal is not for it to react with the substance, but just to increase its rate of reaction. Okay, so let's look at a energy diagram of this. Okay, so if this bottom side is time, okay, meaning like as the reaction is occurring, okay, and this is potential energy, which really means kind of like temperature or heat, however you want to think about it. But let's say we're reacting these two substances, okay, and without any catalysts, okay, a non-catalytic reaction, okay, we don't have a catalyst, just a normal reaction that needs a lot of energy, a lot of heat to make this reaction occur where they combine with each other. Okay, so if there's no interference, we need a lot of energy to get over this kind of hill to make this reaction occur. But if we get this catalyst in here, okay, which is represented with this blue circle, okay, we get this catalyst in here, it gives us a couple more steps, but watch what happens. So first the yellow and the blue are going to react with each other. Okay, this is the first step. And then the blue is going to react with the green, and then the blue is going to kick itself out and make the green and the yellow react together. Okay, so you'll notice there's a lot more steps, right? First it has to react with yellow, then it has to react with green, and then it has to kick itself out. But these energy barriers are a lot less, right? Or the amount of energy you need to get it started is a lot less. So it only has to make a little jump to get to here, then only needs to make a little jump to get to here, and then only needs to make a little jump to get to there. Okay, rather than having to go over this entire energy, I guess you say call it bump, whatever you want to call it, to get to this reaction. Okay, so hopefully this diagram isn't too confusing, but the point is that the catalyst makes more steps, but it makes it easier for the reaction to occur. It takes less energy, less work to get this reaction to occur. And again, the catalyst does not react with the products at the very end. Okay, the catalyst is never consumed with the products. Okay, it acts separate. Okay, it does its job. It gets the things to react with each other, and then it kicks itself out. Okay, and so it never reacts with the products in this reaction. Okay, so again, hopefully that makes sense. But if not, the main thing you want to understand is that the catalyst's job is to make the reaction occur easier and faster. Okay, without actually being absorbed in the reaction. Okay? All right. So that is a catalyst, and again, it increases reaction rate. Let's look at some specific types of reactions. Okay? Let's talk about combustion reactions. These are probably the most commonly known reactions because they're the easiest to see, because we have these nice big flames that usually come out with them. Okay? But we want to make it clear that combustion is not just when oxygen combines with methane. Okay, there's lots of different ways to make a combustion reaction occur. So anytime you light a fire, for example, okay, that is combustion. Anytime you have a gas stove, if you've used a gas stove, that is a combustion reaction. So flames is a good signal that it's a combustion reaction because that's the oxygen igniting. Okay. But I just want to make it clear there's lots of different substances. Methane, propane, butane, those are all gases that can cause combustion reactions. And so, again, anytime you see a flame, that is a sign of a combustion reaction, okay, because that is usually oxygen igniting. Okay? So, we know, we're pretty familiar with combustion reactions because of these, nice expulsion of energy, okay? But we see that as a flame, but let's talk about the reverse, okay? So the reverse of this nice release of energy and heat is what we call an endothermic reaction, okay? So endothermic reactions we're probably not as familiar with, but this is kind of the opposite of a combustion reaction, or this reaction when heat is released. Instead of that heat being released, the reaction actually stores the heat and makes the surroundings cooler, okay? So think of like a cold pack, if you've ever seen these. Not the ones that you put in the fridge, but the ones where you kind of just snap them like a glow stick, and then it instantly cools. Okay, that is an endothermic reaction. That substance is absorbing heat, absorbing energy into the reaction, which makes the surroundings cooler, which makes the ice pack cooler, which you can use to ice your knees or whatever it is. Okay, but that is an endothermic reaction. So um, ice packs are an example. If you've ever done baking soda and vinegar, you'll remember that the bottom of the glass is usually very cold. That's an endothermic reaction. Okay. If you put like ice and salt together, it usually makes the ice a lot colder. I believe that's an endothermic reaction as well. Okay. But it's making the surroundings cooler. Okay. So if we were again to kind of draw the energy, draw the heat. Okay. So if we look at this graph, we start with the reactants down here, and then it absorbs a lot of energy, okay, and puts it into the product. So some people think that means it's making the surroundings warmer, okay, but don't get this confused because this is the substance's energy. Okay, if we were looking at the surroundings had all this energy. Let me make this a different color. Okay, so if we're looking at the surroundings, they had all this energy, okay, but then that energy got absorbed by the reaction. So the surroundings are actually going to cool down, okay, when this reaction occurs. So if this is the surroundings, okay, the surroundings are cooler because the substance is absorbing that heat, is storing that heat, okay. And so hopefully that makes sense. That in order for the substance to get more energy, okay, in order for the substance to get more energy, it has to take that energy from the surroundings, which is going to make them cooler. Okay? So that is an endothermic reaction. Okay? And so again, why it's called endothermic is because if you ever look at the English roots of the words, endo means in, and thermic means heat. So inward heat, basically, it's storing heat, it's bringing that heat, and again, that's going to make the surroundings much colder. Okay. All right. So the opposite of a endothermic reaction is what we call an exothermic reaction. Okay. So an exothermic reaction is probably one we're more common with. This is the opposite effect, is when a reaction releases heat and makes the surroundings hotter. Okay. Exo meaning out and thermic still meaning heat. So outward heat, right? Releasing heat. Okay. And so combustion is an example of an exothermic reaction. Okay. But it's not always a flame. It may just be heating up the surroundings, just like a hand warmer, right? A hand warmer would be an exothermic reaction. It's making your hands warmer by releasing that heat from the reaction. Okay, so if we look at the energy diagram for that, this time the reactants are going to release that heat, making the products have less energy, and so the surroundings are going to have not as much energy, and then suddenly they get all that energy from that reaction, and so the surroundings get warmer. Okay. So there you go. That's the surroundings. And again, I apologize for the poor spelling because I'm using the touchpad, but hopefully you get the point. So again, the reaction releases that heat, the surroundings absorb it, making it warmer. Okay, so there's endothermic, okay, taking in the energy, making the surroundings cooler, and there's exothermic, releasing the energy, making the surroundings warmer. Okay? All right, so there you go. Endo and exothermic. The last term we want to cover is what we call activation energy. Okay? So activation energy. So it's the energy needed to start a reaction. Okay, so energy most commonly used as heat in most reactions. Okay, is what we need to start it. So for example, if you put logs in a fireplace, okay, they just don't spontaneously start on fire and give you a fire, right? You gotta light a match on maybe paper or some kindling, right, to get enough energy to start on fire. Okay. So this reaction doesn't occur just for no reason. Same thing with like hydrogen and oxygen. We know that if we combine hydrogen and oxygen together and then ignite it, we get a combustion reaction. Okay, but if you put hydrogen and oxygen together and you don't light it, they're not just going to start reacting for no reason. Okay, they need some type of energy. Okay, so some reactions need this activation energy, this heat to get them going. Okay, if you don't have this activation energy, they're not going to start. Okay, so usually a match, some type of flame, is what you need to start the reaction. Okay, Same thing with like gasoline in your cars, right? You got to actually start it with the ignition. Okay, your gas doesn't just start combusting for no reason. You got to give it some energy. Okay, so if we looked at a reaction that needs activation energy, okay, it might start down here and it wants to go over here to the products, but it can't do that until it gets over this mountain. It's like if you've ever ridden a roller coaster, right? You got to get those chains to get to the top of the roller coaster ride. Same thing here, okay? That needs some type of energy to get to the top for the reaction. But once it gets there, then it can carry out the reaction with no problem, just like the roller coaster will go through the ride with no problem. Okay, but it's got to get something, or it needs something to get it to the top. Okay, so in the reaction, we need to give it some energy from a flame, some type of light, okay, to get it up here, and then the reaction will occur no problem. Okay, so not every reaction needs an activation energy, but some do. If you need to usually light it or give it some type of heat, that means it needs activation energy. Okay? All right. So that is it for this chapter. Make sure you do the vocabulary review for this chapter. And hopefully that made sense. Let me know if you have any questions, and thank you for watching.